Good afternoon.
Good afternoon, sir.
Yes, sir, it is visible, sir.
Okay, very good. So I think while we wait for other students, we will start that video. Is the audio, are you hearing the audio also?
No, sir.
Okay. So is there a way to start the audio? Or maybe I will talk about that.
Straight gyrus movement.
Okay.
As a matter of fact, it's going to prevent me from trying to move it.
So you have this
in this axis.
axis.
So, start this
You can see 3 degrees of freedom are there. It's able to, you can rotate the wheel, and then you have one more thing. What he has done is he has spun up the wheel in the center. So that is what we are going to do. He is using this motor to spin the central wheel to a reasonably high velocity. So since it is heavy, it has a very good momentum. So now it has 3 degrees of freedom. It has the bottom one, and then the axis can be changed, and then the spin wheel itself is spinning. Okay, so now this is the present position now. He is not able to, he will show you, he's I think stabilizing it for some time. Now you can see, to change the axis of wheel, you can see the orthogonal axis is changing. He is trying to push with his fingers. So when he tries to rotate along that particular axis with
Sir?
his fingers, that is the vertical axis. Yeah.
Sir, your voice is breaking in between, sir, sometimes.
Sir, even the video is playing in sir, pauses, sir. Like it is going on like 250. Like time is there's a 2 second lag in video. We can only see 2 seconds frame, sir.
Some frames are missing, sir. Like,
Yes,
Yeah,
sir.
so I think there is no way I can share this video because this platform is not allowing me to share it fast enough. So
So you can put
maybe
the video
I have
in the
already
chat
put
box.
it in the website. It is already there in the Moodle. So I
Okay,
was expecting that some of you would have seen it.
sir. We have seen couple of videos in the Moodle.
Yeah, this video is also there. This video is also present. Okay, so let us see. Basically, what he is doing is, so now when the axis coincides, it is very easy to spin. You can see with his fingers. But if the rotation axis is orthogonal, then it is very difficult for him to push. So he has to put a lot of force. He is showing that. But when he is trying to do that, you can see that the orthogonal axis will change. So this is the basic principle for the precession, that you apply torque at one axis, but you observe the precession on the orthogonal axis. That is what is being shown here. This is the basic fundamental principle for a gyroscope's working. So the amount of movement, that is the angular movement, will depend on how much force or torque that is being applied on the vertical axis. I know this, most of you are not able to see it properly, but maybe we can talk about it now. So if you look at the, maybe later on you can go back and look at that video. So there are, you can see that three sets of gimbals are there. One, there is an outermost gimbal, that half circle, that's the outermost. You can rotate it with respect to the vertical axis. Vertical axis means the axis on which the plane of the ground. When you keep it straight on top of the ground, with respect to that plane, you have an orthogonal axis, which is your, what I call it as vertical axis. Then there is an inner gimbal, which is rotating with respect to this outer half ring gimbal. Of course, then there is one more gimbal. It is the axis along which the wheel is rotating. So maybe you can ask questions now. I know it is difficult to ask questions. So from here we can pick up for the basic principles of gyro. So when he tries to move the vertical axis, the inner gimbal rotates in the orthogonal axis. You can see the axis along which it changes. That was what is being demonstrated in the video. So that is the basic principle for a gyroscope, and that is what we will be exploiting to do the measurements of the rotation with respect to the vertical axis. So with respect to every particular axis along which you have to sense the rotation, you will be keeping the such kinds of gyroscopes. If you want 3-axis measurement, you will keep 3 such devices. Yeah, those of you, yeah, it's difficult, but let me know whatever you can get out of this. If you have questions, ask. Then it will be easier. Okay, so I'll assume that there are no questions. Let us move on to the slide. Later on also you can ask. Let us so this was the gyroscope video, which is not displayed here, but that was what I was trying to show you. So the basic principles are explained through this diagram. Instead of showing a half ring, here we have shown the full outer ring. That's all. That's the only difference. The axes are shown in different directions. That is another difference. So you can notice that the applied torque direction. So can one of you guess what is the applied torque direction with the video or approximate video, whatever you saw there? The applied torque direction will be which axis? Can you guess that?
Towards up, I think.
Yes, very good. The vertical axis is the upward axis along which you have applied the torque. That means this gimbal was pushed in that. That is your input axis. Okay, and then the precession axis is orthogonal to that. That inner gimbal was free to move with respect to that. So here I think there is a slight difference probably. Let us see if there is a difference. No, I think that should be fine. Yes. Since you have to imagine the outer ring to be a half ring. You imagine that the right part of the axis you have one half, you cut off the other half, then you will be able to imagine that it is very close approximation to that. So when he tries to apply torque along the input axis, you will notice that the inner gimbal will rotate. When you try to put the outer gimbal, the inner gimbal will rotate. That is what is mentioned. So this is the basic principle, and then the quantification is given by the expression shown below. That is, the applied torque is equal to the amount of precession cross product the angular momentum. If they are in the orthogonal direction, multiplication and cross product will be same, because cross product as sine theta. If theta is 90 degrees, then multiplication and cross product will have the same effect. Any questions in this gyroscope working principle?
No, sir.
No. So even later on you can ask, but don't. For the moment, let us go ahead because we are actually significantly behind this here. So we have this optical. Another way to construct the gyroscope is using the optics. So here moving parts can be reduced. So you observe this figure. I hope you can see the mouse pointer now. You have this triangular shape and you have an eyepiece. Eyepiece is the location in which the rays are entering as well as leaving out. So as soon as the ray enters, you split the light or the monochromatic laser beam into two parts, one on the right side, one on the bottom side. It goes around in circle and comes back into the same side. So since the distance traveled by both the rays, that is the split rays which travels around, each of the split rays goes around in the opposite direction and then comes back to the same location. Since they have traveled the same distance, there will be no interference pattern. Now consider a situation in which this triangular shape, what is shown here, is rotated with respect to the central axis, which is shown, which is protruding out of the screen. So this is only the plane section of the device which is shown here. So if there is a rotation, what would happen? One of the rays will take longer distance to travel than the other rays. Is this clear? If there is a rotation effect, and if you have split the light into two parts and allow it to travel in opposite direction along this closed curve, and if the closed curve is rotated with respect to the center here as shown, then one of the rays will take longer distance to travel than the other. If this part is clear, then you will understand that if one of the rays takes longer, then when you receive it at the location, at a particular location, in this particular case, the same location.
Sir, can you repeat what is this? What is the source, sir? Source and which two rays?
The source and the destination are same.
Sir, that
The output is shown here on the right bottom. So that is where the source is also injected. So the source is injected into this medium. You can, so once it is injected into this closed curve, it splits in, there is a mirror on these edges. They are reflective as well as splitting. So it enters this closed area by splitting into two parts. One along the bottom, passing through the glazing medium, and one at the top. In fact, the complete medium is lasing. We are just showing it as this only a schematic of the system. So the light splits into two. Basically, it's a monochromatic light. It splits into one at the bottom, one at the top, and it goes around, crosses each other, and comes back into the same location from which you injected the light. So if there is a mechanism to observe the interference pattern, if this closed shape that is shown here is not opaque,
Sir,
yeah.
sir, your voice is breaking
Yes.
a lot, sir, so it's confusing.
Sir, it's like, sir, you are speaking, then there is a 1 second pause, and then it's overcoming that 1 second loss and speaking again and then again and again. So there is
So
a
we are not
loss.
able to make out what exactly you're trying to say, sir, because of
Yes.
the break.
Okay, so I don't know how to solve this problem.
So can we meet in some other platform?
Google
Yeah,
Meet or Zoom.
yeah, no problem. That will
Soft
be
Teams takes a lot of internet, sir.
Hmm. Teams takes huge amount of bandwidth. I know that we cannot help. These people are forcing us to use this, and then it has an horrible audio. I don't mind. You let me know which platform you want. I can join that immediately. If one of you can share that.
Kshitij, can you create a room or something?
Sir, right now we can use our Zoom link, sir, which we had, sir, earlier.
But is that earlier Zoom link working?
Sir, right now it is working, sir. License is not expired till yet, I think, sir.
Okay, can you put that in the WhatsApp? Sorry, can you put that in the chat box?
Okay, sir.
Are you going to share that now?
Yes, sir. 1 second, sir.
No problem. Take your time.
Sir, I've shared the link.
Okay, I have clicked on that. Wait. I start this video again?
Yes, sir.
Okay.
Good evening. I'm Ed. This is an
Is
egg
the audio
production, and we're going to demonstrate
okay?
spinning. Now, over here, we have a brass gyroscope, toy gyroscope. There's this a brass flywheel that rotates in this axis, and it's on the gimbal. And the gimbal is made to spin around this axis. And also on a vertical axis this way. Now, what I'm about to do is spin this gyroscope using a Dremel with a little rubber wheel on this. And I can get this to spin about anywhere between 3,000 to 6,000 revolutions per minute. And with the gyroscope spinning, it becomes stable and wants to resist movement. As a matter of fact, it's going to prevent me from trying to move it in any in this axis. So here we go. I'm going to start this gyroscope spinning. Again, clockwise from your motion going like this. I also put some spiral marking on the flywheel so you can see that the gyroscope will be moving.
Are there any questions? Someone wanted to ask something?
Sir, actually the video is lagging a lot.
Hmm. Okay. Slightly better than time, but okay.
Voice was fine, sir.
At least, but if you don't see the video, that effect is gone. Let us see. Maybe once again I will share next week.
Sir?
Yeah.
You said it's on model, right?
Yeah, it's already on model.
So one of us can share the screen and play from the model.
Yeah, sure. Please do that.
Can you do that?
I have stopped sharing. Let me check. Hello. Yes, madam. Yes, madam. Yes, yes. Okay. Today or tomorrow I will give this. Thank you.
Sir, can you tell the video name?
Yeah, I'm also searching. Just one moment. Let me see if I can upload it immediately. How did it vanish from here? It was there. I'm uploading now. Just a moment.
Sir, I think this is a video, right?
Yes, yes. Is it there? How did you find that?
Sir, on YouTube. I think.
Good evening. I'm Ned.
Good.
This is an egg chop production, and we're going to demonstrate gyroscope spinning. Over here, we have a
Can you
brass
mute, sir?
gyroscope,
Here
toy
you
gyroscope. There's a brass flywheel that rotates in this axis, and it's on a gimbal, and the gimbal is made to spin around this axis, and also on a vertical axis this way. Now, what I'm about to do is spin this gyroscope using a Dremel with a little rubber wheel on this, and I can get this to spin about anywhere between 3,000 to 6,000 revolutions per minute. And with the gyroscope spinning, it becomes stable and wants to resist movement. As a matter of fact, it's going to prevent me from trying to move it in any in this axis. So here we go. I'm going to start this gyroscope spinning. Again, clockwise from your motion going like this. I also put some spiral marking on the flywheel so you can see that the gyroscope will be moving. All right, here we go. There we go. Now the gyroscope is spinning about 3,000 RPM in this axis. And as you can see, if we try spinning this gyroscope around this axis, it's gonna want to resist movement. Here we go. Let's see what this gyroscope wants to do if we try to spin it in this axis. There we go. I'm going to try pushing the gyroscope the other way, pushing the right hand side of the gyroscope towards you, and you're going to see what it's going to want to do. There we go. Now, if I orient this gyroscope so it's spinning straight up and down, it's going to be very easy to spin it. There we go. But only in that direction. If it becomes dislodged from that direction, it's going to want to resist. There we go. It's going to be very hard to spin it. As you can see my fingers of trying to apply some force, spinning it. And it's very difficult to try to spin it with the gyroscope moving at that speed. Once the gyroscope becomes oriented in this fashion, it's going to be very easy to spin it. There we go. Once it comes out of this orientation, like that,
Yeah, remember this position later on. We will be coming across a situation called gimbal lock situation, where that inner gimbal is no more able to rotate because of the external torque. Please continue.
it's going to be very hard to spin it. There we go. So that concludes our Thank you and good night.
Yeah, thanks. I think you somehow located it. I was searching for that. Yeah. So let me go back to the screen. I hope it is much better understanding after that video. You can now the figure what we show here is capturing the essence of that. So in the figure you had the half ring. Half ring played the role of the outer gimbal. So and then you had the inner gimbal, which was a full ring. That was a inner gimbal, and then the spinning wheel. So you can imagine the spacecraft fixed to the outer part. So if the outer part tries to rotate, then the inner one will rotate. So the measurement of how much the inner one has rotated will give you a feel of how much rotation has occurred in the outer part. Basically, what is the torque applied at the outer part can be measured using the precision in the inner chamber. So that is what this expression is also saying. Torque equals to precision cross product with the angular momentum, which is the spinning wheel. Depending if you have a larger angular momentum, the effect is larger. And then there was also a situation when the axis coincide, when the spin axis coincided with the applied torque axis, you no longer experienced the inner gimbal movement. So that is also called as gimbal lock axis. You can imagine an aircraft or a spacecraft carrying three such things in three different axes. So when to any questions now, you can imagine the situation when the applied torque axis and the spin axis are coinciding, the inner gimbal did not rotate. So if you imagine a spacecraft carrying three different things in three different axes, so whenever the rotation along each of the axis occurs, the inner gimbal along each of the axis will measure the rotation. So that is how the rotation is kept track. So if you imagine a situation when the spin axis is coinciding with the torque axis, you would notice that the precession did not occur. So if the spacecraft turned its orientation so much such that this situation occurred, then what will happen is the spacecraft will no longer be able to detect rotation along that axis. So these situations are real situations. In fact, highly standard launch vehicle may not have so much variations, but if you look at highly maneuverable vehicles, such as your aeroplanes for fighter aircrafts and things like that, and also when you are having a re-entry from the space back to the earth, there is a huge amount of rotation or the torque felt in a particular axis. So this may cause these axes to coincide with each other, and this gimbal lock situation will occur. And it's a real situation. The first moon mission carried such mechanical systems, and then while returning back, they experienced this. Since they had already foreseen such a situation, they manually reset the gimbal to the new location. So that is how they overcome this problem. You should go back and read about this mission. When they return back from the moon, how this gimbal lock situation was avoided. So any questions here? I think now it is more or less clear. If you had seen the video, then if you were able to see the video, those of you who are still not able to see, please see it for yourself from the link Kshitij shared. Thank you, Kshitij.
This rotor is to be rotated.
I'm open for questions. Pardon me?
So this rotor is to be rotated constantly.
Correct.
Right?
Yeah. So there is a spinning wheel has to be spun. Yes, yes. It has to be in constant. So you will have to, yeah, that's a good question. How do you spin this? Because everything else is moving. How do you pass the wires through the spinning system? There are something called slip rings. Slip rings are something through which it can pass electrical contacts through the rotating mechanisms. Basically, it's kind of metal pieces on both sides which will rub against each other. Of course, there will be some reduce, like friction will be there. Friction will reduce your motor efficiency, but that is how it is done. So whenever you have rotating parts and you pass current the central power or electrical connections to the central part. Let us imagine from the outer ring to the inner ring. Then we use something called as the slip rings. You can also go back and have a look at them. So, were you trying to tell that, or you had something else in mind?
No, sir, that done.
Okay. Any questions here? Okay, so if you have questions later on, please come back to me. Now let us go to this optical gyroscope. Another mechanism without a moving part. So in this particular case, if you look at the right hand side, the it is, you have to imagine it as both the source as well as the output part where you are going to destination. So the light enters into the triangular region. The arrows indicate the direction of the light travel. It, initially, when it enters from the right hand bottom side, it splits into two parts and goes in opposite, not really opposite direction, in an angular direction. Here, if it is if the angles are if it is a regular triangle, then you split it into 60 degrees, and then it goes around these flat objects here are also called reflectors. They reflect their light to the direction which is required, which is shown here. So they go around and come back to the same location. When the light reaches back at the same location, you look at the interference pattern. If the interference pattern does not indicate any change, it means that the path length taken by both the light beams are same. So therefore, interference pattern is not. You won't see any interference pattern there. So, however, if you allow this part to rotate along with the complete setup, then what would happen is one of the light ray will take a longer distance to travel and reach back to the same location when compared to the other light path. Along the direction of rotation, the light takes longer amount of time because the output piece from which the input was taken would have moved to a newer the light rays which are reaching the destination have two different paths. Even though they started with the same phase, they will arrive at different phase. So this difference in phase will appear as interference pattern. So depending on the width of the interference pattern and how they are moving, you can measure what is the rotation rate of the system. These are called optical gyroscopes. Any questions here?
Sir, when the setup is rotating, the
Yes,
mirrors are also rotating.
Mirrors are also rotating. Correct. Everything is a rigid body. Everything rotates.
So then
Only
how are you?
since light is traveling, right? Tell me.
So then how are you?
Question is, so why should it, right? How are we saying, because light
Travels in straight.
if it is a standard right, light follows that this thing, no principle. What is that principle of relativity? Yeah? Which says that even when the medium moves, it is actually in the apparent inertial or whatever space the light is moving. So it takes the same amount of the speed of the light is same, even though the distances traveled by the light will be different here. It is not like an object in the train. When you throw the ball, then the ball is suppose if the train is moving, the ball's speed also would have to be accounted for when the train is moving. No, that is not the situation here. Here, what is happening is the behavior of the light is different. That is what you have to imagine now. I think even otherwise, one of the light rays have to travel far longer distance than the other one. I think we don't have to invoke that principle at all here. Yeah. It's only when you are looking at time dilatation or something. I think it's a standard experiment. You imagine the entire triangular setup is rotating with respect to the center where the omega is shown. So you started the light at T1. So along the direction of the rotation, by the time it reaches your output location would have moved. So it will take longer time. But for the other path, you are receiving the light at an earlier point of time. I think we don't have to invoke that principle. Yes. So one path takes longer, one path takes smaller. So using this, you will be able to notice the interference pattern, which indicates how much rotation has taken place. So this is optical gyroscope. This is how it appears. The complete path you can see it is glowing with a laser beam moving inside. So left hand side is one axis gyroscope, right hand side you can see that at three different axes, three different gyroscopes have been orthogonally placed. So this complete pack will be kept inside the launch vehicle. We will go into the details later on required. But right now, I'm just introducing you to these sensors. Any question? This is just a basic principle. This is called Sagnac principle. It's a very important optical principle used in measuring rotation, as well as it has many other applications, like it cancels out certain noises and things which are very good in the optics. Okay, so then we come to something called GPS, which we have been using, or we should say GNSS, Global Navigation Satellite System. GPS is one implementation of this system. So you have to imagine that there are multiple satellites in the sky. The positions of the satellite are known. So if you have your mobile phone, all of your mobile phone are having this GPS. The satellites are transmitting the signals. You are receiving the signal and computing your position. But satellite is not transmitting your position, it is transmitting only its position. So what is being computed in your mobile phone is distance from yourself to the satellite. So once you know where the satellite is and the distance to that, you will know around the sphere around which the user location is placed. distance of the satellite to the user. That is what is computed by your mobile phone. There is something called CDMA based transmission, code division, multiple access using some correlation properties. We will go into that. You can estimate the distance to the satellite. Once you know how far away you are from the satellite, you know the sphere around which the user is. So now one satellite is not enough to identify your location. There is an ambiguity around the sphere. What is usually done is you use one more measurement from another. If you use two satellites, then you will be your position will be known with respect to this red colored circle. Similarly, one can use more satellite to finally find out the position. Actually, what happens here will be there will be 2 points, that is intersection, 2 circles will be there. In the case of 3 spheres, which is shown on the top right here. However, one of the points can be easily discarded by claiming that some one point will be on the surface of the earth, another will be not on the surface of the earth. So if you have 4 satellite measurements, you can find that out, which is shown okay on the figure bottom. So you can see the images. If you have only one satellite, you are around the sphere. If you have 2 satellites, you know your position with around the circle. If you have 3 satellites, you know with respect to 2 points. Even here, it is easily 1 point can be eliminated. However, if you want one more satellites measurement, you can always use that. But what is usually done is the 4th satellite is used to understand the time, that is position is measured, and then the time. So time is important because satellites carry atomic clock. You will not be carrying atomic clock, you will be carrying only quartz crystals, which are prone to drift. So in order to even compute the time with respect to atomic clock, you can use the satellite systems. So this is what is done in the global navigation system. Later on, we will go into the details. This is just a basic principle based on the trilateration principle. The position of satellite is known, and the distance to the satellite is estimated using certain CDMA techniques, correlation techniques. Any questions here? It's too early to ask, but maybe there are some.
Sir, with 3 satellites, can we transmit the time.
Yes.
They can
No, 3 satellites you will not understand the time. The fourth satellite. The bias with respect to the atomic clock is measured, and that you add as a compensation to your quartz clock. That will be the estimate. For that you require the 4 satellite.
Sir, I couldn't understand the reason why, sir.
Sir, I couldn't understand the reason why, sir.
You couldn't understand the reason. What? Can you tell that? Rephrase that question to me.
I couldn't understand why would we need 4 satellites to measure time also, like to get the time also. Like if we have atomic clock in each of the satellites, then like any satellite can transmit us the right time, right? Hello, sir. Am I audible?
Yeah, sorry, you are audible. See, the satellite is not directly transmitting the time. Even if it transmits the time, how long the time has elapsed from the satellite, that is not really known, right? So therefore, you cannot directly use that information. What is usually done is you will be running one more replica clock in your receiver. The replica clock will try to keep track of the satellite clock. But your replica clock is made of usually quartz crystals. So these cannot precisely reproduce the timing as good as the atomic clocks. Therefore, what will happen is your replica clock will be drifting. So the difference between your replica clock and the satellite clock is what is usually computed in the navigation algorithm. So when we write down the equation, that part will become clear. So you will be trying to keep track of the satellite time by computing how much you have drifted. That drift will come out of the solution of the fourth satellite equation.
Okay, sir.
Okay, so maybe vaguely, it's very vague. I know it's slightly more involved to explain it, but this is the best I can maybe Aditya can do better. He did little bit of this thing in the beginning. Okay,
And
so let us move to what we have. Yeah, yes.
Sir, we have a class right now.
We have another class, no? I will stop the class.
Yes, sir.
Yeah, the class is over now. Thank you for
Today is Janmashtami, sir.
attending. Yeah, sure. So you don't want the afternoon lab. Okay.
Yes, sir, if it is possible.
We will have it tomorrow. Okay. So today, anyway, I will try to see if I can do it better with my.
Sir, there is a
You
problem.
could have told me earlier. Pardon me, I didn't hear.
Sir, there is a problem with the internet connection. The internet connection which you are using is not able to support the Teams or Zoom properly.
So, see, let us see, maybe tomorrow it will be better. I'll go to the office there and make it better.
Okay, sir.
Yeah, happy Janmashtami to everyone.
Thank you, sir.
Happy Janmashtami, sir.
Thank you.